Thanks, yeah. Originally I put in for a talk and a BOF, and then it got changed to a talk and a tutorial, so this talk is about the compilery bits, and then the next half is going to be more of a bit of a tutorial of a BOF with a bit of introduction stuff about how modules would interact with the rest of the tool system. There we go, right. Right, okay, yeah, so I'm going to start with some background on what the modules proposals look like. Just out of question, who was not here for my talk last year in Prague about modules? Okay, quite a few. And of those that didn't put your hand up, who can actually remember what I said? Right, okay. So I will, yeah, I'll start from scratch and assume that you are unaware of the modules thing, so with some examples. Then I'll talk a bit about the internals of the compiler in terms of how stuff's squirted out to disk and read back in again, and some of the changes I've made there since I talked last year. And then there's this atomic thing, which I will get to. Something about the progression to how this will get into the C++ standard. And if we've got time at the end, some statistics. And that's why it's something atomic, because there's an S word. Right, yeah. So the wiki page here shows the current state of development, and I remember to update it. All this stuff that I'm going to talk about is on the C++ modules branch of the repository. You can go and download it and build it, and it'll work to various degrees. But it's all experimental, so it's going to change. It's brittle, that kind of stuff of warnings. Okay, so we'll start with how you as a user would use a thing that was delivered to you as a module. Import, new keyword. Import name of module, semicolon. These names are essentially dotted sequences of identifiers, and they're in a different naming space to namespace names. Okay, so you can call the module foo, and you can have a variable called exactly the same spelling, and it'll still work, and you will be confused, but it'll work. So I'm importing two modules, and then somewhere in my code I can call these functions that are made visible by these two modules. They don't have to have any particular name. You probably want to give them some kind of name so you know where they came from in the usual sort of namespace name thing, but it doesn't enforce any of that stuff. You can have multiple modules exporting the same names in the same namespace and same names of the same overload set, so long as they don't all have the same signature. That kind of thing. I'm going to use anything that you can declare can be exported. So functions, types, type defs, namespaces, I forget what else there is in C++, but templates, yeah, oh, it has templates, yeah. One of the things that happens is if you use some internal foo function that it didn't export, you will get a compile error. It'll not make that name will not be visible to you, even though it's used internally in foo and may have what you might think of as external linkage. And not necessarily a static thing. If foo was delivered as a header file, header files leak stuff in there about their implementation which you can accidentally use, and that's bad and horrible, and one of the things that modules will avoid, and one of the motivating features for modules is that you no longer have leaking of implementation details that either cause you to have to either lock your implementation down and restrict you in changing how you want to implement things because the user will start relying on it, or users accidentally rely on it, or it pollutes or you as a user, it pollutes your namespace because it got injected and you then can't use this name because somebody else picked it first and you've included their header file. Similarly, yeah, so this is the name. I can declare something with exactly the same prototype, for instance, that something in foo is, and foo didn't export this thing, I'm okay. Foo may be using this thing internally, it's just fine, because I will see different decals. There may be cases where I see both of them inside foo, if to do with template instantiation stuff, which I might get onto, and then you'll get an ambiguity. But generally, it provides name isolation. Okay. So that's you as a user of a module. A declaration of a module comes in two pieces. Sorry, question?
Yeah, when you get ambiguity, is there any way to resolve the ambiguity? Can you somehow qualify the name you want to import so you can decide between different modules that provide it?
Right, so the question is, as a user of a module, do I have control over the names from the module I've chosen to use? Do I have control over which subset of that names I may see? And the answer is no. The author of the module controls which names become visible, and that's the only point they do. So if you get an ambiguity, you'll get a compile error, and you, the user of module, will have this problem. Now, the template case where this happens is in argument-dependent lookup, where the semantics are not entirely nailed down because of questions like you've just asked. So my answer may actually turn out to be maybe. In regular non-argument-dependent lookup calls and uses of this thing, you will not see collisions unless two modules have decided to export the same signature, and then you've just got the same old incompatibility you had with two header files that have decided to give you the same prototype.
Well, that's pretty bad.
I mean, Fortran resolves this by allowing to rename the imported symbols.
Right. Well, we already have namespaces to solve that problem. But I just want to point out, these things are not, these names are orthogonal to namespaces. Right? We can get into some of the unknowns later on as well, actually.
Are macros exported?
I will get onto that later.
Sorry.
Okay. This is modules 101, not 201. Okay. Right. So the way you declare, you provide a module is by providing an interface for it, which is a regular translation unit source file, which just begins with export module foo. So this is module foo, and it's exporting stuff. It's the interface. There's exactly one of these per module. Okay. And it can declare things and define things that are only visible inside the module itself, like this accumulator variable doesn't say export in front of it, so it's only visible with inside module foo. But it's visible inside module foo in all the translation units of module foo, not just this one. So it's not like being static. Here, export int frob, so that's exporting a function declaration that importers of this module can go and call, and it'll do normal overload resolution if there's more frobs around. This is the static int unused, which is only visible inside this translation unit in the normal way that statics is only visible inside a single translation unit. And I don't use it here, so it's unused. You presumably get a compiler warning. And out of this thing, when you compile this as a module, you will get a regular object file. And in this case, that regular object file is going to have a bit of assembly to allocate this variable, because that's where this variable is defined. It may have other stuff, but in this particular case, it's just going to have that. Okay. We're also going to squirt out something else, which is the module definition, a binary module interface, which I'll get onto into a bit, which is part of the. Although you do not have to do this, because the standard doesn't say you have to do this, you would be dumb not to, because that's the way you get better compile times. And a bunch of implementation units that can provide the implementation of foo. So this is, I say, that I'm part of module foo, it doesn't have the export keyword in front of it. And there can be many of these, including 0 of these. And so here, this one part of module foo, so it now immediately sees all the declarations in the interface that are either exported or have module linkage, like this accumulator thing. It won't see this static because statics aren't visible outside of the translation unit. And we're just providing a definition for this function that we want to make visible. Okay. So you may want to have several of these for splitting your module up across source files in the usual way you split a library up across source files. None of those semantics change. But there is a thing you can do, what you can't do with a header file, is this. Here I've got an interface that's also implementation. So I've got an interface that's making this frob thing visible to importers of this, but I've also got the definition of the frob function right in the interface. Right? I can't do this with a header file because I'd end up with multiple definitions of frob in everything that included the header file. It's not in line, see? So when I compile this particular interface, I'm going to get a thing for the accumulator and an actual body of frob being emitted as assembly code. Right. So that's enough bit of module syntax. So we got two. So we got two new keywords, which is module and import, and we're reusing a deprecated keyword export. Export was added in C++ 98 to deal with separate compilation of templates. Turned out to be really hard to implement. EDG implemented it and then had to lie down and said, yeah, this is really hard. I don't think anybody else implemented it in a front end, and it got deprecated and removed in C++ 11, or around then. Anyway, so it's now an unused keyword, so it's now being reused. Hooray. Okay, so binary module interface. This is the thing that gets emitted by the compiler when it's compiling a module interface unit and gets read in by the compiler that's processing an import statement. And the whole reason you want to do it this way is that it means you do not have to reparse all the modules, all the module interface units when you import them. With hash includes, you have to reparse all the include stuff every time you hash include it. And that can end up with several 100,000 lines of code, followed by your, 200 lines of code that you wrote. So most of the code is reparsing these header files that don't change much or change infrequently. So that's quite a compilation cost we would like to remove, and this is one of the motivating features of modules. So we have this binary module interface here. So this is my picture of a build. We have some implementation source units, an interface source unit, some user code. Compile these things down into object files and link them in the usual way to get an archive, static or dynamic. Don't really care at this point. Not interesting. Rather than if this was using header file include technology, this would be a header file. It's not. It's a module interface unit. So I compile it and get object file out of it. So this
Nathan, one question. Why does it have to be binary?
It doesn't.
Okay.
Okay. It's the name we've decided that has fallen into use is a binary module interface because it happens to be, and we've had discussions about should this. I will get into it in the. Save that thought to the next talk. Right. When I'm using this as a user, I have my source code that's got an import statement. This compiler has to read the BMI to be able to generate the object file, link it together in a user way, get an executable, right? Now there's a problem that you've probably all wondered about is given a module import statement that just said import foo, how do I find this BMI? I've got this magic box, okay? For the purposes of this talk, this is a magic box, okay? Just assume it does what we need. Yes. Don't worry about the contents of the box. It'll distract you. We'll get onto that later. Okay. So, Now I'm going to talk about some of the implementation inside the compiler that I have at the moment. And those of you who weren't here and those of you who don't recall won't remember that I talked about essentially two different things. One was name lookup, namespace name lookup changes in the compiler, and is why I went away and rewrote namespace name lookup because it was horrible. Through accidents of history of how the history of GCC, if you take a C compiler and turn it into a C++ compiler and namespaces are rare, you end up where we were. Namespaces are not rare anymore, and it was horrible. Now it's nicer, I think. And that has not changed since I redid it in terms of the moduleness stuff. We now on each namespace binding end up with a sparse array of namespace bindings, but that's a fairly trivial change. The other piece that I talked about was the serialization of all the declarations that are made visible. We have to write things out and read them back in again. And unlike precompiled headers, we have to merge these declarations between different imports. We can import any bunch of stuff. Imports can be recursive. They can't be circular. So the import dependency graph is a directed acyclic graph. It's not. So unlike header files, which you can play tricks with the preprocessor and get them to be mutually inclusive, and as long as you break the inclusivity in some way, that's not true with modules. PCH works in the compiler by essentially squirting out, it's a memory dump, an annotated memory dump of the compiler's image after it's included the first hash include. So it works in a world where you say hash include everything in all your code, and everything doesn't change between all your compilations. That's not what we're doing here. So the serialization of writing out stuff, we want to write, when we write out a module BMI of the module interface that we're declaring, we only want to write out the bits that we've actually declared in this translation unit. And bits that we're referring to from other modules, because we imported them, we want to do by some kind of reference or some kind of, and not actually take the actual decal object and serialize it. We have to sort of do some referencing in some way. And I talked about a tree serializer where I had essentially had a handwritten serializer of the trees that knew where to stop. When it referred to something from a different module, it would squirt out a name reference kind of a thing or tag. But in terms of circular references in the internal structure of the dependency graph that you have, it had to deal with loops there because that's how the GCC data structures are. And if you think about it, if you're squirting out an inline function that's recursive, you kind of have some kind of recursion there. So you have to deal with back references and the like. But I had a tree serializer. I serialize the AST. I don't serialize Gimple. I'm before the Gimplification stage. Because we need this stuff that the importers can then go and reinstantiate templates or whatever. So it's all at the at the front end representation level. What else did we have? Oh, right, yeah. And essentially what I'm writing out was a single blob of stuff. There was some metadata in there that I'd sort of fudged up to look a little bit like trees, so it could write it out. And where are I? Now, and then when I got to sort of beginning of this year, I started thinking about how the next, or after actually, yeah, so at the end of last year, I'd pretty much got everything working. I could serialize templates and functions and classes and class templates and member templates of classes and all that stuff and enumerations. And type defs was the thing I checked in on 2nd of January, which was my goal for last year. And that kind of made it usable in a way that you could kick the tires and it wouldn't, the wheels wouldn't fall off every time. But then I started thinking about how to do location information because I'd just punted on that. And it was getting more and more awkward to add additional features to this big blob of data that I had. And one of the comments last year, he's not in the room, was from Ian Taylor saying that lazy loading was important for Go modules. And I was thinking, lazy loading, yeah. That would be a good thing to do, because if we're trying to improve compiled performance, lazy loading is clearly a good thing. These BMIs could get very large, and if you read them, you have to read them all in every time you do immediately as you do the import, but only use one thing from them. That seems a little unwieldy. And one of the ways of thinking about what I've done here is just imagine what the web would be like if we didn't have TCP and HTTP and HTML as three separate layers in the protocol, but just had one big blob of stuff there. It would be horrible. That's what I'd done. I had just merged the transport layer and the transmission layer and the application layer all together, and it worked for a year. Anyway, so I was thinking about this and said, okay, I need some kind of file format that I can have separate blocks of data, and I can index them and page them in as I need to and the like. And I thought, yeah, I know a form that does that. But then I thought, yeah, not every system has that. So I designed this format, encapsulated lazy records of named declarations, because I wanted lazy loading, and I'm naming the declarations, that's how they're keyed. Those of you who know your toolkit will know that Elrond, well, right, now, David is not in the audience, I think, either, because there's at least one system that doesn't use ELF, so don't worry. If you know your Tolkien well enough. So, all I actually needed was this section, named sections, and index sections. I don't need symbols, I don't need segments, I don't need machine descriptions or any of that stuff. And one advantage of making this format very much like this format is tool reuse. I do not have to write my new introspectors to look at my binary module interface file when I'm trying to figure out what it looks like. I can just do that. This README section is a human readable README that's kind of interesting. This stuff here is the actual declarations, and the names there are for human consumption. So I can tell you that that's the declaration of counter, that's the definition of a thing called HWM, that's the definition of a thing called get, because it's got squiggly braces on the end. I'll get into exactly what's in there in a bit. But here's all the metadata that we end up reading for when you do an import. This is a configuration to know, oh, am I compiling for the same architecture? Am I got the same set of flags that are important, that kind of stuff. Here's some location information. Here's the set of namespaces. Here's the binding value, the set of bindings. So for each particular namespace, a set of namespace names that have names, and they end up pointing back to these things here, which I end up accessing by index. So if this was proper ELF, I've cheated here, because these sections are not renumberable arbitrarily. If you renumber things, it'll break, but you're not going to do that. Right, yeah. So yes, and we can look inside the README file. Oh, right, yes. Originally, I was just reading and writing this with regular file I/O, but then Richard Smith pointed out that, well, Clang does it by mapping it. Okay, then. So while we were in Rapperswil, I implemented mem mapping things. So when you do an import, this whole chunk of stuff is mapped with file back storage, so it's just address space. I'm not taking up, well, it's pageable memory, but it obviously doesn't go to swap. Page it all in, and then I can just access this via the mmap interface, and similarly with writing it out. I only need to really optimize reading. Writing only happens once when you're doing a module interface unit. Reading happens on every import, and on every import you if you haven't imported the thing before, because you may import it multiple times, only the first one counts, we end up actually examining this stuff here, and this is all the lazy loading stuff. Although there's many more of these in this particular case, these things are much bigger, so hooray. Right, yes. And you can look at the README file, the README section, and I give you some information about how this thing was built. I'm very paranoid with version numbers at the moment. The version number of the tool is based on the date the CP directory was last touched. Because otherwise I'm just going to get confused by errors where I'm mismatched versions of the compiler because I just rebuilt it half an hour ago and forgot. Okay, so how does the lazy loading actually work? We have here, so if you really want to go, obviously objump, you can actually look at the bytes, but yeah, that's pretty unintelligible, and even to me. But I did use that once. Right, so, as I said, cross-module references. References from one module to another are done essentially by the namespace name. I write out the namespace. The namespace name itself is referenced by name all the way down to the global namespace. So I end up looking up in the target module. I know what target module I'm looking up because that's part of the data that's stored out. A particular name, and if it's an overload set, I know which number on that overload set it is. So overload sets are not reordered within a module when you read them back in again. And it would be nice if references within the module itself to things that were also done that way, and that allows me to lazily load them. Jason has a question.
If the module you're importing is changed to add to the overload set.
Sorry, how? Oh, right, yeah. So here in this config, what I do, I generate there's a CRC I generate as I write this whole thing out and store it in here. And when I write when one of these things, there's also the import table in here as well, and that stores the CRC it saw when it read that module in. So if you get a one level down, which is the case I think you mean, because that's the case that's important, you should hit it because you get a CRC mismatch. I'm not trying to be cryptographically strong or anything like that, but you know, it should catch this kind of errors.
Mm.
Yeah.
So if a module you import changes, then you need to rebuild.
You need to
your
rebuild.
module.
If you're a module interface unit and you import a module and that module changes, you need to rebuild yourself before you can be used. Yeah?
Okay.
Just this, do I understand this? Can you split the definition of a namespace between modules?
Yes.
So effectively, you said they were orthogonal, but then you're talking about qualifying lookup within a module.
Right. Yes. The answer to your question is yeah. Namespaces pervade across all modules. Okay. Now there's excitement with the anonymous namespace, which I probably won't get into, but actually that doesn't matter. So on each binding in a namespace, if foo in the global namespace has got declarations attached to it in two different modules, there'll be a vector of names attached to foo in the namespace lookup machinery. And I'll say I want the definition from module 1 or I want the definition from module 2, right? Now, when you're doing namespace such lookup in your source code that you're parsing, you'll actually get some union of those things because you'll have imported those things. But there could be indirect imports that you don't see bound to that name, so it gets kind of interesting. There's a bit mask that tells you what to do. In this case here, with the lazy loading here, I know which index on that vector I want to load. There's a remapping because when you're imported, you won't be imported as the primary module because you're not anymore. So there's a remap vector, so but that's trivial to look up. So you know which one of you can find this thing unambiguously, even though namespaces are across modules.
Okay, so from the point of view of when you wrote it, you wrote foo, and then inside the foo file you wrote namespace bar. But in terms of actually processing it, the bar is taken outside,
The
and then
bar
foo
is
is a qualification on top of
ye-
that.
Yeah, namespace is a bit odd in term unique from other declarations in that they cross modules. They have this kind of unique property that you do not want to shard the namespaces in each module, because then you end up with a whole bunch of lookups rather than just one lookup and then go bing bing, I want those things. Okay? So the granularity is the namespace binding, and if I want a class that's in a namespace, I end up looking at getting the class. If I want a class member, obviously I have to find the class first, so this hierarchy thing just naturally works. Where have we got? Right, yes. So this would be all fine and dandy. I'd look at a namespace binding and write out the binding of the set of names on that name, and I would carry on to the next lazy section. But this is C++, and you're all expecting me to say template at this point, aren't you? You're wrong. You don't even need to get into template land to find circular dependencies. This bit of code declares two functions, foo and bar, each of which has a default argument of calling the other one with an argument, right? I have no idea why you want to write this code, but you can. So when we're writing out the declaration of bar, we somehow need to refer to foo, and when we're writing out the declaration of foo, we somehow have to refer to bar. But the more interesting point is when we read in the declaration of foo because we used it, we also going to have to read in the declaration of bar. And so, it would be tricky to put these in different blobs of laziness, but there's no point, because when we get one, we're going to have to get the other one too anyway. So we may as well put these in the same lazy blob. And what I'm getting to, we need to somehow walk the declaration graph of stuff, including bodies of inline functions and templates and all that kind of stuff, to see what they refer to, and build some kind of dependency graph, and then partition it into strongly connected clusters, which are these things. Foo and bar are in the same strongly connected cluster because there's a loop between them. Whereas if they then called some other function that didn't reference them, then that would be a dependency. Now, because I work for a company that knows a little bit about graphs, somebody told me this is the way of solving this problem. Because it's actually the same problem as finding loops in control flow diagrams, but I didn't really think of it that way because it looked different to me. But this is the same algorithm. Tarjan's algorithm, it's in Knuth, and apparently he likes it as a nice algorithm. And it is a very nice algorithm. It scales according to the number of edges in the graph. And another nice feature is it orders the dependencies before the thing that depends on them. So you then end up with not only finding these strongly connected clusters, but the things that you can order the nodes that they depend on. So that means we can order the lazy loading and know that if we ever have to backtrack and load a thing that's got a higher index number, this graph is corrupt and something has gone wrong, and we're not stuck in an infinite loop. And we might be stuck in an infinite loop, so we should stop because we shouldn't have generated this. And then lookup happens on demand. When I use a name in the source that I'm writing, it will find one of these. It will look up in the namespace slot, find, oh, this thing hasn't been loaded. I better go lazy load it before I return from the namespace lookup. And you want that check to be really cheap. So what I actually do is place a cookie in the binding slot. The binding slot is a tree pointer, and I can distinguish it from non-tree pointers because I assume rationally that trees are aligned to at least a 2-byte boundary. So I set the bottom bit, and if the bottom bit is set, then this is a cookie, a magic cookie that I send back. It's actually the index into the module, into that section table, and go load it. And that in itself may cause further lookups that go up that tree or into other modules and the like, but I know that lookup will terminate and actually not end up in a loop by construction. So that all kind of works, which is great. And it found some bugs in my cross-module reference stuff, because there are some pieces of the tree that aren't named, and I'm looking at you, binfos. And I was actually cloning binfos across across modules. Binfos are the base information stuff of a class hierarchy. So I had to, I need to deal with them carefully and actually reference the class they're a binfo, the most derived class they're a binfo of, and encode how you find the specific binfo that I wanted. There are another couple of cases, but anyway. So this was all got me lazy loading, and then also fixed a bunch of bugs that would have been harder and confusing later on. So hooray. Now, there are things that cannot be named in C++. This is the thing. So C++ 11 added the auto keyword, or reused it for a different purpose, because nobody used it for its original purpose anymore, where I can declare a function without actually naming the return type. And in this function, I'm returning an object of some structure that I declared inside the scope of the function. Why am I doing that? Well, and I'm exporting this so people can call it. So they clearly need to know how the thing that's calling them needs to have a reference handle to this name thing. Well, if it's a lambda, if I'm returning a lambda, this is a very boring lambda, that's essentially morally equivalent to this bit of code here. And people write this all the time. And they normally use them as inline functions, but you don't actually have to have them in inline functions with modules going on. So there we go. And you might have an indirect reference through another module that's doing that. So, you know, I have to somehow refer to this type here without using its name, because I can't look it up inside this function, because I may not have the function body because it wasn't in line. So I find these things during that partitioning walk that I just described. I also find these things because if I'm writing out the declaration of foo, or walking the declaration of foo, not the body of foo, just the declaration, and I find a type or an entity that is somewhere within the body of this foo function because its context is there, I go, oh, it's one of these things. I need to do something special. And all I do is find them during the partitioning walk. They fall into the lazy loading scheme quite nicely, but then I build an array of them and use an explicit index and have them as escapes there. Okay? And that is how the Voldemort type array thing works. And Alex has a question.
How is this different from naming a type that is not exported in the interface of a function?
Right. Yeah. So a name that's not exported may end up in that table. It can be put in that table, but it won't have a bit on it to saying this is actually visible to other modules, because you actually end up needing to do that. Because, as I said, in the first example, I declared that ACC variable, but then I could refer to it in one of the implementation units. So clearly there was a name ACC somewhere, or a reference to that variable somewhere, and I just do that in exactly the same way. It's just that, yeah, sorry, there's a new flag on each decal that says, is this exported or not? And there's also a new field in a decal saying which module it belongs to that deals with all this. I kind of haven't described that, but yeah. Right. So that's enough about internals of the compiler. I'm now going to talk about competing standards. And this is where I changed my slides a bit yesterday, so what am I doing? Right. This is answering the question of how do we get to a nice modular world from where we are now with header files? Because we can't put hash includes inside the module interface unit, because then all the members of that would just become members of that particular module, and this is clearly broken. So the TS has this thing called the global module. And it's a little bit before the module declaration itself, where you say module semicolon for reasons, and you put all your regular hash includes down there. And that means that I can then refer to things in string inside here without bits of string becoming part of foo. Okay? So I can export std string from jar, and then the users of this somehow will know about string as a type, but they don't know about it as a name because I haven't actually exported string, because I can't. They will have, if they want to manipulate this type in any way other than use auto, they will have to hash include string as well in some way. Okay? Right. So that kind of works. I haven't implemented any of this, by the way. But if you think about it, it means that every compilation of this module will textually include all these header files. And I say these header files are enormous. You get like 300,000 lines of code just here. And that sounds an unfortunate situation to be in. And you end up with a merging problem across different modules. Right, yeah. Oh, and there's one global module that all these things belong to, but you've got to get different views on it depending on what you hash included here. And so, you know, it's a little bit confusing. Yeah, expensive to parse all these headers, and it's expensive to merge them because two different modules may end up including string, referring to string in some way, and then I've got two sort of definitions or declarations of string that I have to merge somehow and know they're the same. And that's obviously going to be a complex merge thing in the same way that precompiled headers don't do this because it's expensive. So this was a proposal earlier this year from Richard Smith based on other work and stuff, but he put it all together. And it was another take on modules. It was an accidental acronym because it then needed a name, and he realized, oh, hang on, it's got a name. And it has a couple of differences. One of which is we have all the imports at the beginning of the module. Now, in the examples I showed, I just did that naturally because that seems sensible. But in the TS, you can actually import anywhere as long as it's the global namespace, further on down. And that also gives merging problems that which are unpleasant. But it fixes some problems as well, so it's not completely strange. So we put all the imports right at the beginning. And then the first thing that isn't an import ends this preamble. And it's at that point that all these imports become visible, all these things that these are exporting. So I can import this. I've got a funny import here where I've kind of used a header file, but in an import with a semicolon on the end. Right? I get onto how this actually gets constructed later on in a couple of slides. But essentially, it has to be sort of modular-ish already. And none of its macro, it doesn't see macro, it doesn't get infected by macros from where it's being imported from, and its macros only become visible down here. So that means, you know, I can do these in any order and stuff, and that makes a bunch of stuff better. Right, yeah, you get a special compile mode for these modular headers. You end up saying, and this is implemented, okay? I'll just finish my sentence and get to you. It's quite, yeah, so I can compile, it's like when you compile a precompiled header, that you can compile one of these as a module with module legacy and you get a thing, and it does export macros from these things. And a human must have determined that it's sufficiently modular to work, right? And in practice, that is true for a lot of stuff. It's sufficiently true that this is very similar to the way Clang modules actually work. And the reason they do it this way is it really cuts down on your build time because you only compile this thing once, effectively, and then import it. And importing is much, much cheaper than actually parsing it. Jonathan? Okay. Right. Another bit that the Atom thing has is module partitions. This is a question, if I've got two mutually recursive classes, for instance, that refer, or types that refer to each other, but I want to put them in different sources because that's a useful way of organizing my source code. I can't do that in the TS. Well, I can't easily do that in the TS. I have to put them in different modules. And then in the TS, I've got the cross-module equivalent of extern, where I say extern module foo. See, this is basically saying, there's a module foo, and it's going to declare this thing, just believe me. And this is like, you know, back in the days when KNR was the thing, and nobody has hash included unistud, you put extern int exit brackets or parentheses, and that was good enough, right? And you know, nobody does that anymore, and there's reason nobody does that anymore. So this smells unfortunate. We don't do that in the Atom proposal. What it does is this: you can partition the interface across multiple source files, so there's not one interface. You know, this is a partition that's got a colon to separate it from the main name. This is a partition of module Bob. But one of these partitions are only visible within module Bob. As you step back from module Bob as a user, you only see the things that there's a main interface that it says, oh, these parts of me are now visible. So it's not, the granularity disappears when you step away from the module itself. And this allows the implementer to move things around between parts of Bob without breaking ABIs or APIs and manglings and stuff things. Right. Yes, and you turn on module the atom mode by f modules atom instead of f modules ts. Okay. Right. So how's this getting into standards? So So the atom thing was published in March this year, if I recall, and then it was decided to merge parts, merge it with the TS document, which was published earlier in the year, as a working document. And by merge, I mean decide which pieces we wanted, and which pieces we didn't want, and which pieces of the TS should be thrown out. So some TS disappeared, and some bits of atom went in. But that's not a completed discussion. But at least it's, I think it's moving in the right direction. Later this month, there's a modules workshop because we need to figure out some other stuff like argument-dependent lookup and precisely what we want here in some cases. There's a meeting in San Diego which starts on November the 5th, and Ville has pointed out that's a very appropriate date for arguing about stuff, which is pretty much the gating point at which to decide what of this could get into C++20. Which may well be some subset of this merged document. I don't think the whole merged document is going to get in. But it should be enough to be useful. Right, and failing that, February 2019, but then it's going to miss the boat on C++20. Right, so GCC, we're going to go into stage 3 sometime later this year, probably November, to get GCC 9 out in April. The bits I haven't got done, as I haven't got legacy modules done, I've got the mode working, I've got macro import and export working, I haven't got merging of decals between things, which I need to do. And I need to fine-tune some of the name lookup stuff that I've just been talking about, because some of it turns out to be not working this way. Partitions, the complexity there is actually going to be with the merging, so it's going to have a lot of similarity with modules, with the legacy modules. So I expect partitions not to be as complicated as just doing them on their own, because there's commonality. This argument-dependent lookup stuff requires a path of instantiation to be thought about, and the rules are not thought completely through. Global module is again this merging problem, but there are some ambiguities about the desired semantics there, so I'm not sure of that. But anyway, that's quite a chunk of work to do between now and November, I guess, particularly as we don't really know what the semantics we want are. So, yeah, right. I don't know. And Jason's going to render an opinion. Yay.
I was wondering if you've done anything with kind of reachable properties nonsense.
The reachable properties nonsense is gone.
Oh, good.
That's one of the outcomes of this merged document. So the merged document essentially matches the implementation of my graph walking stuff. And that's coincidental because the merged document was Richard Smith and Gaby Dos Reis working together to figure that out, whereas I independently had to go and implement this stuff, and it just so happens, oh look, they're similar. Hooray.
Hooray.
Yeah.
I know you said you were going to talk about macros later, but it's bugging me. What happens if somebody declares a macro outside your module declaration?
Right. Okay, yeah, I didn't actually get onto macros, so well done for catching me. The macros are not exported from a module. A module interface unit can define macros, but they're only visible in that module interface translation unit. They don't get further. The Atom proposal did have the ability to export macros, but that's not in the merged document, right? So this is a thing that could happen later on, but it's not going to happen now. The legacy headers, or legacy modules, export all their macros. And because otherwise it just wouldn't work, because headers export macros. And if they don't, then there are some reasons I'll get into in the next discussion, actually, but
It was kind of also the point that in multiple compilation units, conceivably somebody could declare an external macro which affects what happens inside a header differently in two different TUs.
Right. Yes.
Right.
Okay. That problem is if you're doing that, you're going to lose because you compile the legacy modules exactly once, and you can pass hash defines in on the command line as you so desire. But essentially, you have to say they all operate in the same mode. So if you want to set, what is it, underbar POSIX 500 or whatever, you do it once when you compile it, and then everybody gets that mode. And again, in practice, that's probably what you want. That works sufficiently well to be good enough. And if you think about it, if you're compiling your headers in different modes, but then merging them into the same program, yeah, you're fragile to start with. One of the nice things about the legacy module thing is that whenever I have a ponder and I think, how should this bit of legacy modules work? I go back to, well, if these were headers, this would happen. Okay. And one of the outputs of that is that, well, if this doesn't work with headers or is ambiguous or fragile, well, yeah, it's still going to be that way. I'm not going to try hard to make headers magically modules. They just need to be modular enough to get there from where we are.
Have you thought about the possibility of parameterizing modules on the import line, which would give you some of the possibilities that you had with importing things and having them dependent on hash defines?
No. Okay, so when I say, so all the stuff that I've been presented by, this is pieces of, the TS was a point in time of a proposed technical standard or addition to the C++ standard that's been worked on by more than just me. And there's no desire to do something like what you've described. It's basically, if I'm giving you an interface, it's the thing I'm giving you. You don't get to pick and choose. If you want to pick and choose, you need to talk to me about breaking my interface up in some way. But yeah, if you want to pick and choose from my interface, no. Right? That's kind of the mental model there.
I understand that the module name is an identifier, right? Are there any recommended practices to avoid name clashes between different code bases?
No, and that's an ongoing discussion within the tooling subgroup of the standard committee, which is actively discussing that at the moment, and I'll probably get into that in a bit in the next talk. So yeah, but it's an open question at the moment.
Yeah, just one remark. I mean, Fortran has modules which are a little bit different, but did you actually look at what we do there and how it could be useful in your context? Like things like selecting only certain variables, for example, to avoid pollution or renaming on reload or something?
I have not. I don't know what things other people looked at when originally drafting the TS. A lot of the TS was written before I started looking at this stuff. Although, I've contributed quite a lot to how it's moved on from where it started from. Okay.
Should our modules intend to be some way portable between compilers?
The BMIs, that's a topic for the next talk. Okay.
What I was going to ask earlier, I decided wasn't relevant to everyone, but actually I think maybe it's so where you could do import of a header. Mm-hmm. You mentioned that that header is not affected by macros defined before it, so it's a sort of way of isolating a header from other rubbish, and the stuff after it doesn't leak out of the module, does it?
Correct.
Can you do import with a header outside of a module?
Yes.
So
the preamble that I showed, I did actually show it. The preamble I did show with a module declaration at the beginning, but it didn't need the module declaration.
Okay.
If it's not a module, it would still have a preamble that would just consist of import statements, right? And one of those imports could be .io.h. If you
So this actually gives us a nicer way of including headers that are sort of a bit more isolated from. Cool.
Yes.
I wanted to know if that was usable outside of modules, and if not, could you make it so as the GCC extension?
Right.
But
yes, no, it is, and that's
Cool.
Yeah, like I say, at the moment you can use the legacy modules in GCC. The macros work. What doesn't work is if you import two different legacy modules that declare the same type, which is completely legal C. I then explode because I go, yeah, I don't know how to merge these at this point because that's my next bit of roadmap. Okay. Oh yeah, David.
I have a question about diagnostics, but I suspect you're going to talk about this in the next talk. If, for example, you import a module and then call it incorrectly, like you pass in a bad argument for parameter 2 of a function. So are you tracking source location in the modules? I think
Yes.
I saw yeah.
Yeah, so that was the next thing I did after the lazy loading stuff. I wanted to get that locked down because I knew that would have things. So in Atom, I haven't got it working for complexity reasons I probably need to actually address. But in Atom, you get full location information for, I haven't done macro location, but that's because I haven't implemented that bit. There's no technical reason why that won't work. But you get the line information and column, if it's not in the macro expansion, it all works across modules, and it basically says, in module X, imported at line foo dot, 15 of foo.c, that is module Y that was imported, you get this. You get the full sort of trace back working quite nicely.
Excellent. And that's in your branch already?
That's in my branch at the moment, and
Excellent.
there are test cases of it. I can show you some of that if you're even more interested.
How much more difficult does it make to debug problems in, say, template
right,
code?
yes. It makes it, at the moment, it's very difficult to debug because there is no debug information. Well, I can't remember when the debug information is emitted, but I basically don't deal with that at the moment. So when I've had to debug these things, I've been, and generally my test cases are, yeah, this thing linked and ran to completion, or this thing exploded in some way. And mostly they explode, and then just inspection of the assembly code go, yeah, I know what happened there. But that's the thing I have. Okay, so on my list of things I haven't done, thank you for finding a gap. Okay, well, I've got to the end of the first hour. We have a few little gaps. I've got some statistics on the branch development, which we could do in the intermission if you want to know. Yeah, okay. Because basically it's my own private branch, because nobody else is writing to it. I looked and still looked at the commits that I had. So this is going from last January up until the end of last month. This green graph is the number of added lines per month. This month was when I was actually working on the name lookup branch and fixing name lookup, and also on vacation, so nothing happened there. This is where I managed to remove stuff. This blue line here is the delta of number of lines added plus number of lines taken away. So you can see I've changed my mind a lot. This red line is number of fix-me's per 10,000 lines of code, right? And we're down at about 60 fix-me's, and the rest of this is just lines in the sources that I've changed, not including the test suite. And the rest of the C++ front end is down at about 3 per 10,000 lines. Okay. And this is code size. So this is the absolute number of fix-me's is about 90 at the moment. Number of lines of code has gone up to, just under 14,000. Number of lines written and then deleted and added again is about 5 or 6 times bigger than this. So I'm doing better than Sturgeon's law, which said that 90% of everything is crap. But it's rather, I would write bits of code and then come back and rethink them. And it was very nice being able to just do that on a private branch without having to worry about making bigger patches. I would commit early and commit often because that made progress. Yeah. Oh, right, yeah. But the other thing, my code's not reviewed by anybody, so I tend to write stuff like that. Okay, let's have a 5-minute break before the next talk. So we'll start again at 16:40.